Hello, my name is Janelle Applewhite, and welcome to my Module 2 presentation. So our agenda for today is that we'll first be discussing reliability and validity, and we'll move into classical test theory, which is very crucial to this module. It will be demonstrated via hand calculation practice, and then lastly we will discuss hypothesis testing in relation to social camouflaging. Now we're looking at reliability and validity. So when we think of reliability, we want to ensure that our measure yields consistent results, or how precise this is in terms of, does our measure, given the sample or given different samples, would it yield consistent results? And this is very crucial to trying to figure out, does our measure or instrument capture the construct that we're trying to examine. Validity is also pertinent to this process, which it deals with the accuracy of our results. Is it correct? Similarly, there are numerous forms of validity which should be taken into account depending on your research. We have criterion validity, face validity, construct validity, which deals with does our measure construct deals with does our measure measure what we intend, what it is our intended construct that we're looking at. All right, now looking at our hand calculations, you can see we have on the top left corner an image of data related to camouflaging in autism, and we have 5 variables being masking, compensation, and so forth. For these, we use this to calculate Cronbach's alpha as a demonstration by hand. And as you can see, we calculated our key components, which would be sum scores, our means and standard deviations. In our top right hand corner of the image, you can see we calculated our variance for each individual item. We also calculated the standard deviation for those, as you can see it's circled. In our third middle image, you can see we calculated covariance and correlation, which are integral steps to calculating alpha. And correlation, inter-item correlation, deals with how the items are related to one another and considers factors. If one item is dropped, would it impact the others or the accuracy of our measure? In the very right image, you see Cronbach's alpha has 2 formulas, but we chose the one that uses sum score variance and the sum score variance of the individual items. And from there we calculated, we got a Cronbach's alpha of 0.82, which would be considered pretty good by standard. Now, in the bottom 2 left images, we have effect size and power. Effect size and power are components of statistical testing. And when we look at effect size gives us the magnitude of if our data is meaningful. Whereas, for example, as we go further down, hypothesis testing does not determine how meaningful something is. So effect size, it's more representative of if we want to find meaningful differences. So from that, we would take the variables we want to look at. So we looked at masking and compensation, and from there, we divided our means of these variables by our pool standard deviation, which in essence is variance. And from there, we got an effect size of 0.16, which by standard is not considered meaningful. So you can see that immediately. If we were looking for meaningful differences, this would be a problem. Now, when we're looking at power, it relates to having the ability to correctly reject the null hypothesis, which is important in hypothesis testing. However, power it can be influenced by numerous factors such as sample size, effect size, and significance level. And the lower your significance level is, the lower the chances of you finding a significant difference. Now, power is usually calculated priori or prior to collecting your data because it gives you one step ahead. Oftentimes, calculating power afterwards may not be considered preferred. But in this case, we calculated our power based off if we had our effect size and sample size, and from that we got our power of 0.06, which is very significantly small. So because of this small power value, we are definitely, if we further in interpreting our data, we are going to have issues in correctly rejecting the null hypothesis. So now we're looking at classical test theory, and it must be noted that it is a theory, but it gives us some account of that our observed score is equal to our true score plus some error. Another way that it can be phrased is that our observed score variance is equal to our true score variance plus our error variance. So what we see on the manifest level is related to an underlying true score, but there is some error accounted for in that. Lord has it as a ratio. Our reliability is our true score variance to our observed score variance, and variance is an important factor because if we decrease our variance, we increase our reliability and vice versa. So let's talk about hypothesis testing and the types of errors in research. So here we have a matrix which is crucial to hypothesis testing and understanding the type of errors we can make. And what we see here is, for example, we are going to test the hypothesis if two of our variables are significantly positively correlated. So that would be our alternative hypothesis. The null hypothesis would be that it is not significantly positively correlated. As such, this matrix displays what happens if we reject the null and what if we fail to reject the null. So in the first corner, you can see type 1 errors, which can occur if we reject the null, but the null is true. And with failing to reject the null and the null is false, meaning that there was a significant differences, but you failed to reject the null, you have committed a type 2 error, which is something we try to minimize in our studies. So here you can see we have data from our study on social camouflaging in autism. This top right left image relates to the camouflaging autistic traits questionnaire, and what we can see here is that we have 30 observations across 11 scaled items, and what this measures are different forms of camouflaging, and the scores from teenagers we collected from ages 13 to 16. You can see our means are primarily negative, however standard deviations ranges from 0.5 to approximately 0.9. So in order to check the reliability of our measure, we decided to conduct a Cronbach's alpha, and what this basically looks at is the internal consistency between our items. So we had a value of 0.93, which is considered high by standards. And what this means is the higher internal consistency, you can be rest assured to an extent that your items, your measure is reliable. However, according to Cortina, alpha, this internal consistency is not sufficient to assess how overall good a scale is. So you also need to consider validity when you are looking at measures to be implemented. Furthermore, in our bottom image, you can see that you're looking at the reliability if an item is dropped. Based on this, I would not recommend dropping items because this can affect the reliability of a measure. So you can see, even though the reliability it's 0.92, which is pretty good according to standard, I don't recommend dropping any items. All right, so back to our hypothesis testing. We were looking at, as I mentioned earlier, masking and compensation, and as such we hypothesized that we would have significantly positive correlations based on the fact that our data is normatively distributed. As such, when we conducted our Pearson's product correlation, our results showed that we had a significantly negatively correlated relationship between masking and compensation. Looking at these sample estimates, you can see the correlation is negative 0.5, which exists on a scale of -1 to +1. However, there is the component of the p-value indicating that there is statistical significance. I just wanted to note that p-value, according to Cohen, it has an inhibitory nature. It does not tell us much about what is happening. It does not indicate anything relevant to meaningfulness of your data. So our p-values is just that, and its standard usually starts at 0.05. So in this situation, we have failed to reject the null, and such we have committed a type 2 error. Now we also have to consider that there may be issues in our measure and what auxiliary factors may have contributed to this. So in the future, we can probably look at, according to Dawes, he talks about having a variety of scales in order to increase the accuracy of results. So that is one direction we can take in revising our measure. So this comes to the end of my presentation. Thank you.